All right, kiddos, today we're going to tackle section 4.6, solving trigonometric equations, part 2. And we have a couple of objectives. Number 1 on our objective list is to solve trigonometric equations involving multiple angles. We are going to solve the equations of the quadratic type using the quadratic formula. And we're going to use technology to solve trigonometric equations. Specifically in this case today, we're going to use Desmos as opposed to your graphing calculator, but you could also do this on your graphing calculator. All right, so we are going to do the problem 2 cosine 3t minus 1 equals 0. So when we look at this problem, it really doesn't look that much different from what we've been doing until you look at this right here. And this is where the multiple angle part comes in. So when we think about what happened when we graph these problems, the parent function of cosine, one full cycle, looks something like this and went to 2 pi. However, that 3 changes the period. So now between 0 and 2 pi, we actually have 3 full cycles of this graph. So normally, if we want a solution, so maybe this equals 1/2. So let's go ahead and solve this actually. So I still have to isolate the part of the problem that has a cosine. So I'm going to move my 1 over to the other side and divide by 2. So over here, I am looking at cosine of 3t equals 1/2. So normally I would come to my unit circle and I would say, all right, cosine represents the x-coordinate. The x-coordinate is 1/2 right here at pi over 3, and right here at 5 pi over 3. So normally I would just write x equals pi over 3, x equals 5 pi over 3. However, I don't have an x here. I have a 3t. So now I'm going to say that 3t equals pi over 3. And I'm also going to say that 3t equals 5 pi over 3. So the only thing that has changed is instead of using a single variable right here behind the cosine, we now have a multiple angle. So we have to use that instead of the single variable. If I use my math skills, I'm going to multiply this side by 1/3, and I'm going to multiply this side by 1/3. Over here, my 3's cancel, and t equals pi over 9. Same thing's going to happen over here on the right. In order to get rid of that 3, I'm going to multiply each side by 1/3. So when I do my math, I get t equals 5 pi over 9. Now, you also have to remember that the period of this graph is 2 pi over 3, not pi, or not 2 pi. So when we do all solutions, we're going to have to account for that. So going back to my graphs, if t is 1/2, normally t is 1/2 would be right here, and you would have 2 solutions. You would have a solution at pi over 3 and 5 pi over 3. But now between 0 and 2 pi, when I look at this particular problem, I don't have 2 solutions. I have 3 times as many solutions. So I have 3 times 2 solutions, which is 6 total solutions between 0 and 2 pi. I can accommodate this without using all 6 of those, because if I think of my period adjustment right here, if I take my first solution and I think of the period between here and here, this is going to be 2 pi over 3, just like this point from here to here is also going to be 2 pi over 3. So if I use that in my solution, it will really make a difference. So to find all solutions, I'm going to take pi over 9, and I'm going to add my period, 2 pi over 3 times n. And then I'm also going to have
Jackson, Drew, Stanley, please report to the main office.
Pi over 9. I'm sorry, not pi over 9. I'm going to have 5 pi over 9 plus 2 pi over 3 times n. Now, there is one other way you could have tackled this particular problem. I'm just going to look at one of the solutions. You could have said that 3t equals pi over 3, and we could have added the normal period 2 pi n. Then when you come in and you multiply by the 1/3, you would have gotten t equals pi over 9 plus 2 pi over 3 times n, and that would have accommodated for the period change from the very beginning of the problem. So at some point you have to accommodate for the change in period when your b value is not 1. I don't really care if you do it on the front end or on the back end, it's just going to have to be done. All right, so let's take this next problem. 0 equals 3 tangent x over 2 plus 3. When I look at what's going on here, the first thing I'm going to do is take this 3 and move it to the other side. So I get negative 3 equals 3 tangent of x over 2. I am looking to get the tangent by itself, so negative 1 equals the tangent of x over 2. And again, if I think about what this x over 2 does, it is a horizontal stretch. So I'm taking the graph and I'm stretching it from left to right like an accordion. So if I go back to my unit circle and I think, okay, well, tangent is negative in quadrant 2 and in quadrant 4. Because the period of tangent is pi, I really only need to look at the top half of the unit circle. And tangent is negative 1 when the x and the y value are identical, and that happens right here at 3 pi over 4. So now, if I think about what's happening, I have that x over 2 equals 3 pi over 4. This time I'm going to show you what happens if you account for your period at the beginning. Right now, the period of the normal tangent function is pi, so I'm just going to go ahead and do plus pi n right here. In order to get x by itself, I'm going to multiply everything in here by 2. So over on the left side, those two 2's cancel out and leave me with x. 3 over 4 times 2 is going to be 3 pi over 2. Then I distribute it here, plus 2 pi n, and that is going to be the only answer I have to worry about. So just remember again from yesterday, when you see all, you're going to have to add the period times n, and if you do that before you deal with the multiple angle, you can use the original period, and then the period change is dealt with when you do your algebra. All right, so you're going to have some problems on your homework where it says use a graphing utility. On this particular problem, I use Desmos because I think it is significantly easier to find the points of intersection. However, you can do the same thing using your graphing calculator. So we have the problem sine x equals 3 cosine x. So I went to Desmos, and in my y1, I put, or my first equation, I put y equals sine of x. And in my second equation, I put y equals 3 cosine of x. When you look at your graph, the first graph is the sine, or the red graph is the sine of x, and the blue graph is a graph of 3 cosine of x. If you look at your graph, these two graphs intersect in 2 different points. They intersect right here where the x value is 1.249, and they intersect right here where the x value is 4.391. We can tell that this is approximately correct because if we think back, the value of pi halves is 1.57, and the value of 3 pi over 2 is 4.51. So when I look at that and I think about 1.2 and 4.3, those are approximately in the right place. When you're on Desmos, if you'll just hover your cursor over this point, then this will pop up. And it just happens that those two x values are your solutions. So you have 1.249 as a solution, and you have 4.391. Now, I will tell you one thing I did in Desmos. I went to the little settings cog up in the top right corner, and I made my x go from 0 to 2 pi. So right here, x is 0, and right here, x is 2 pi, because that was the domain restriction given in the problems in the book. So you might want to go ahead and make that adjustment. That way what you see on your screen is all that you see. If you want to do this on your TI-84 graphing calculator, you can do that. You'll just have to use the key sequence second calc, and then you'll go to like I think it's INT for intersection of the two graphs. All right, moving on. All right, Problem D, our fourth example, is a quadratic equation, sine squared x minus 3 sine x minus 2 equals 0. So when I look at the equation, 3 sine squared x minus 3 sine x minus 2 equals 0, if I came over here and I tried to just factor the quadratic polynomial x squared minus 3x minus 2, I'm looking at that thinking it's going to factor, but we kind of hit a glitch right here, because in order to get this negative 3 here, I need this to be a negative over here, x minus 1. However, when I multiply negative 2 times negative 1, I don't get a negative 2. So at this point, this is not a factorable equation. So I'm going to come here and I'm going to do the quadratic formula. So if I think of what my values are for A, B, and C, A equals 1, B is negative 3, and C is negative 2. Normally when we sing our quadratic formula song, x equals negative b, it's not going to be just x, because like this example over here, I don't have just x, I actually have the sine of x. So you're going to have the sine of x. So sine of x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I don't have a calculator with me, so I'm going to just work this by hand real fast. So sine of x equals 3 plus or minus the square root of 4 times negative 2 is going to be positive 8. So the square root of 17 all over 2. So I am looking at that, and at this point you can put it in the calculator, or you can just leave this at this point. So if I solve for x, I'm going to have to get rid of this sign right here. So we have learned in a previous unit that in order to undo sine, we need to take the sine inverse of both sides. So really x is going to equal the sine inverse of 3 plus the square root of 17 over 2. And x is going to equal the sine inverse of 3 minus the square root of 17 all over 2. You could technically put those in the calculator, and you probably will need to do that just to make sure that if you have a domain restriction, that the values fall into the domain restriction. So you should end up with 2 solutions. All right, next problem. Okie dokie. So for our last example, we are going to deal with problems where the values are not special values on the unit circle. They're just other random values on my unit circle. So we have the problem secant squared x minus 2 tangent x equals 4. My first issue is here I have a secant and here I have a tangent, and I don't like dealing with both of them. So I'm going to attempt to get them all to become tangents. I know from my identities note card that secant squared x is going to be tangent squared x plus 1 minus 2 tangent x equals 4. I have tangent squares, I have tangents, so because I have squares and regular tangents, I'm just going to move everything to the same side and factor. So on the left here I have tangent squared x minus 2 tangent of x. And if I subtract 4, that's going to give me a minus 3 equals 0. Bringing down the equal 0 is important because that is part of the problem. So now I'm going to look at this problem and I'm going to determine whether it will factor. I hope it does factor because it's easier to me than the quadratic formula problems. So tangent squared, what gives me tangent squared? Well, tangent x times the tangent of x will give me tangent squared x. The only thing that gives me 3 is 1 and 3. I need a negative 2 right here, so this is going to become negative, and this is going to become positive. So negative 3 tangent x plus 1 tangent x gives me my middle term, negative 2 tangent of x. I'm going to use the multiplicative property of 0, so if the tangent of x minus 3 equals 0, then the answer is going to be 0. And if the tangent of x plus 1 is 0, then this equals 0. You cannot skip this step. It needs to look just like this. Do not take shortcuts. Don't go skip to go, whatever. Make sure you show your work here. So here I have tangent of x equals 3. Here I have tangent of x equals -1. So if I ask myself, when does tangent of x equal 3 on my unit circle? Well, tangent of x can have a y value of 3. So if you think of the graph of tangent, okay, you could have a y value of 3 right here. It does work. It's just not a special value on my unit circle. So at this point, the only way to get this by itself is to come in here and either take the arctan or the tangent inverse of both sides. So I'm going to take the tangent inverse of both sides. So at this point, x is going to equal tangent inverse of 3. And then I need to add my period, so I'm going to add pi in to that solution. So I really just get tangent inverse equals the arctan of 3 plus the period times n, and that is one of my solutions. And here, the tangent of x equals -1. The tangent is going to be negative in quadrant 2. I don't need to worry about 3 and 4 because the period is only pi, because tangent repeats itself every pi radians. This occurs when the x and the y value have the same number. So here at 3 pi over 4, we have an x and a y that are the same with different signs. So here, x is going to equal 3 pi over 4 plus your period times n. All right, those are your notes for today. If you have any questions, please make note of them, highlight them, sticky note them in your notes, and we will address them when we get to class tomorrow. Otherwise, have a great evening, and I look forward to seeing you tomorrow. Bye-bye.